The constraints of the superconducting wire. The self-limiting nature of superconductivity. The most remarkable property of a superconductor is also its fundamental limitation. The immense electrical current it can carry generates a magnetic field so powerful it abruptly terminates the material's superconducting state. This self-negating paradox is the core, often ignored reason why the dream of a lossless global power grid remains a monumental engineering challenge. A conclusion firmly rooted in the principles of condensed matter physics. This analysis will deconstruct the unforgiving triad of critical limits: temperature, current, and magnetic field. It exposes the vast gap between the theoretical promise of these materials and their practical application in public infrastructure. The popular discourse surrounding superconductivity fundamentally misinterprets the phenomenon, reducing a complex state of matter to a single, easily digestible metric: the critical temperature, Tc. This singular focus on achieving zero resistance at room temperature, while tantalizing, ignores the non-negotiable physical reality that governs all known superconducting materials. Superconductivity is not a simple binary state toggled by heat, but a fragile and conditional phase that can only exist within a strictly defined three-dimensional parameter space, often visualized by physicists as a critical surface. Any operational point that falls outside this bounded volume results in an immediate and abrupt phase transition of the superconducting state. The first dimension of this space is, indeed, the critical temperature, the thermal ceiling, above which a material's atomic lattice vibrates with too much energy to permit the formation of Cooper pairs, the electron couplings responsible for resistance-free current flow. Below this Tc, superconductivity becomes possible, but it is by no means guaranteed. The second, equally critical constraint is the critical magnetic field, Hc, which represents the maximum external magnetic field a material can withstand before its superconductivity is extinguished. This is a direct consequence of the Meissner effect, the defining characteristic where a superconductor actively expels magnetic fields from its interior. When the external field becomes too strong, it forcibly penetrates the material and collapses the delicate quantum state. The third and perhaps most vital parameter for any practical application is the critical current density, Jc, which defines the maximum amount of electrical current the material can transport per unit of cross-sectional area. This limit is intrinsically linked to the critical magnetic field, as any current flowing through a wire, by Ampere's law, generates its own concentric magnetic field. As the current approaches the material's Jc limit, this self-generated field approaches the Hc limit, pushing the material to the brink of its own destruction. Decades of research in condensed matter physics, from the foundational BCS theory that describes conventional superconductors to empirical analysis of high-temperature cuprates in publications like Nature Materials, have consistently demonstrated the unforgiving interdependence of these three variables. Operating a superconductor close to its critical temperature, for instance, dramatically reduces its tolerance for both magnetic fields and current, shrinking the operational volume. Therefore, a hypothetical material with a high Tc but a low Hc or Jc would be functionally useless for high-power applications. The transition out of the superconducting state, known as a quench, is not a gradual degradation but an abrupt phase change, releasing the massive stored energy in a rapid thermal dissipation as the material's normal electrical resistance instantly returns. Superconductivity is therefore not defined by a single temperature threshold, but by a fragile, three-dimensional volume bounded by the interdependent limits of temperature, current, and magnetic field. The central premise for deploying a room temperature superconductor in public infrastructure, specifically for lossless power transmission, collapses under the weight of a fundamental constraint embedded within the laws of electromagnetism. This self-defeating loop arises from the direct conflict between the material's function and the conditions required for its survival. According to Ampere's law, a foundational principle of electromagnetism, any conductor carrying a current is automatically encircled by a proportional magnetic field. The colossal currents necessary for grid-scale energy transport, on the order of thousands of amperes, would therefore generate an immense and localized magnetic field within and around the superconducting wire. This self-induced field would inevitably surpass the material's intrinsic critical magnetic field, Hc, the threshold beyond which the Meissner effect is overwhelmed and the superconducting state is rapidly suppressed. Consequently, the superconductor, in the very act of performing its intended high-current task, creates the precise conditions that define its operational ceiling. While this describes the sharp transition in Type 1 superconductors, the more advanced Type 2 materials used in high-field applications introduce a more complex, but ultimately no more forgiving, reality. As detailed in extensive research within publications like the IEEE transactions on applied superconductivity, these materials tolerate partial magnetic field penetration in the form of quantized flux vortices. To achieve a high critical current density, JC, material scientists intentionally introduce microscopic defects into the material's crystal lattice to pin these vortices, preventing their movement, which would otherwise cause energy dissipation. However, this flux pinning is an engineering mitigation, not a circumvention of the underlying physics. The transported current exerts a Lorentz force on these pinned vortices. As the current increases, this force eventually becomes strong enough to rip the vortices free from their pinning sites, triggering a rapid transition of vortex motion, a sudden return of resistance, and a thermal quench. The very mechanism that allows for high current tolerance contains its own breaking point, ensuring that even a perfect room temperature material is shackled by a formidable performance threshold far below the requirements of a global power grid. The act of transmitting grid-scale electrical current through a superconductor generates an internal magnetic force sufficient to destroy its own resistance-free state. Beyond the constraints imposed by fundamental electromagnetic theory, the practical application of any prospective room temperature superconductor to a global power grid is confronted by two equally formidable engineering challenges: profound material fragility and an intrinsic incompatibility with our existing electrical infrastructure. Research from materials science centers, including the Max Planck Institute for Solid-State Research, consistently highlights that the most promising high-temperature superconducting candidates, particularly the complex cuprate ceramics, are notoriously brittle. These materials possess mechanical properties more akin to fine china than to the ductile copper or aluminum currently used for power transmission, making them fundamentally unsuited for being drawn into the flexible, durable wires required to span continents. The manufacturing process of creating thousands of kilometers of uniform superconducting tape, spooling it for transport, and deploying it across varied terrain, while ensuring it can withstand decades of thermal cycling, ground vibration, and mechanical stress without fracturing, represents a material science problem of immense and potentially insurmountable scale. Even a minor crack or imperfection can disrupt the superconducting path, leading to a localized quench with potentially significant operational disruptions for the grid segment. Compounding this mechanical challenge is an even more fundamental electrical incompatibility. Our global power grids operate almost exclusively on alternating current, a C. Yet superconductors exhibit their hallmark of zero electrical resistance only for direct current, DC. When subjected to a C, a superconductor is not lossless. The continuously oscillating flow of the alternating current generates a perpetually fluctuating magnetic field, which in turn forces the magnetic flux vortices within the material to move, causing dissipative energy losses through hysteresis, as confirmed by extensive analysis from bodies like the Electric Power Research Institute, EPRI. This AC loss mechanism means that even a theoretical room temperature superconductor would still waste energy when integrated into the existing grid, thereby negating its primary proposed advantage. A perfect room temperature superconductor still presents significant integration challenges for existing power grids due to its inherent material brittleness and its unavoidable energy losses when carrying alternating current. The cumulative weight of these established physical principles and obdurate engineering realities leads to a definitive conclusion. The discovery of a room temperature superconductor, while a landmark achievement in condensed matter physics, would not represent a panacea for global energy infrastructure. The intricate and unforgiving relationship between critical current density, Jc, and critical magnetic field, Hc, establishes a fundamental ceiling on power transmission capacity, while the inherent mechanical brittleness of advanced superconducting ceramics and their energy dissipating incompatibility with alternating current, a C, systems present profound, and perhaps permanent, practical barriers. The popular narrative, replete with visions of magnetically levitating mass transit and zero-loss energy grids, is therefore not an aspirational future, but a fundamental misapplication of the technology's true potential. The ultimate value of these extraordinary materials lies not in the wholesale replacement of copper for bulk power transmission, but in their capacity to revolutionize specialized, high-value applications where their unique properties can be exploited within strictly controlled environments that do not violate their operational limits. We see this demonstrated in existing applications where superconductors are already indispensable. The powerful magnets in medical magnetic resonance imaging, MRI, machines, for example, function precisely because they use a stable direct current to generate a massive static magnetic field in a mechanically inert setting. Similarly, the electromagnets steering particle beams in accelerators, like the Large Hadron Collider at CERN, rely on superconducting wires operating with direct current under cryogenic conditions, a far cry from the dynamic and hostile environment of a national power line. The emerging field of quantum computing further illustrates this point, where superconducting circuits are a leading platform, but they operate at near absolute zero temperatures and handle minuscule levels of current in environments meticulously shielded from stray magnetic fields. In all these successful deployments, the technology is leveraged for its ability to sustain immense current densities without resistance, to create powerful magnetic fields or sensitive quantum states, all within a controlled, depowered, and mechanically stable system. The true value of superconductivity is realized not in its broad application to public infrastructure, but in its precise and revolutionary impact on specialized scientific and medical instruments operating within tightly controlled physical parameters. The self-negating paradox at the heart of superconductivity is therefore not an engineering hurdle to be overcome, but a fundamental physical limitation. This internal contradiction, where the current required for grid-scale power inevitably generates a field that destroys the superconducting state, confirms that these materials are primarily suited for specialized applications rather than broad public infrastructure. The promise of the impossible wire is ultimately grounded by the unyielding laws of electromagnetism. If you appreciate this level of in-depth analysis, please consider supporting Tech Dissect Official by subscribing. Given that a room temperature superconductor is not a viable solution for our energy grid, what alternative material or system do you believe holds the most realistic potential for revolutionizing global power transmission? Thank you for watching. We'll see you in the next deep dive, where we'll investigate why the solid-state battery revolution is still decades away from your electric vehicle.